Morning.
Hey, good morning.
I do like my t-shirt. It's
Oh,
very
that's
competitive, all these
awesome.
t-shirts. You
When
have the
to?
coolest backgrounds. In this course and in my online course, which I'll use today, uh, we say nasty things about people who do SVD. And I'll kind of try to explain it. I'll tell you a little bit about a linear way of thinking. And I got divorced from that a long time ago, but not everybody has. Linear thinkers. And it's just like bad music, it's seductive. So linear thinkers think in the first approximation, everything is boom, a line. Or generalizations, they're called plane, hyperplane. And for example, the linear version of thinking about neurons and neural networks was that there's a high dimensional space and neurons have to identify something in that high dimensional space. And how do they do it? They put various planes through that space, hyperplanes, and they find the region of hyperplane where I have only cows and another one in which I have only oranges. And, they solve problems by that. Now, there was an original perceptor and it was killed a long time ago in the 50s, well, 60s, not 50s. There's another version of linear thinking, which is, harder to deal with. And they say nature is noisy, neurons are noisy. So what actually happens, it is not that what our data looks like a line. What our data looks like, it looks like a cloud of points because, there's noise and we're supposed to extract information from the noise. And that's what we did with SVD last week. I was too lazy to draw the picture, but, one of the links has very nice pictures of ellipsoids. So what we do with data is say we're given some coordinates, but then SVD says, well, no, you should go someplace else and you should turn your coordinates. That's the rotation V. And then everything will sit in ellipsoid. Ellipsoid is naturally described by correlations. By the way, normal modes were also described by this. And that's how you understand things that look complex and complicated, nonlinear. Now, this is so unspeakably wrong about nonlinear problems. I don't know even where to start. But basically what happens in nonlinear problems, linear problems, everything is X. And it might have an index if I'm in number of dimensions. Now, nonlinear thinking, which started seriously in mid-60s, that says, to understand problems in which what you will do depends on your state where you are, you have to kind of multiply your state with what you want to do. So you have to at least start with X squared. This is, the simplest possible nonlinear problem. Now what the X squared does, if you have a function that's X squared, if you have a function X squared, what it does is that if you start with a line, what does X squared do? It stretches that line and then it maps both the positive part of the line. So this is negative, positive. The typical shape that when you do the baby thinking nonlinear way is that you have to think of horseshoes rather than arrows. In other words, a nonlinear data, even when it's noisy, is going to look like something that's bent. It'll be a manifold which is curved. And now, what I object to when SVD people try to do their magic stuff is they say, oh, I know how to do this. You have some noisy crap. What I'll do is I'll put an ellipsoid. And then the most important point of the ellipsoid is, of course, the center, because I know that from here, right? The most important is the center, and then I have some stretching and noise. So the nonlinear people tell me that whereas thing is happening on a curved manifold, I'm supposed to take linear average of that manifold and look what happens in the center and deviations from it. What can I say? Kindly, I can say that's wrong. That's not how to think about this. So that's why the second half of this week, we actually go and look at some nonlinear problems. You know, it's subtle. The way you get a feeling for it is, and that's why I'll ask you to do some numerical simulations. You know, people just didn't have intuition about this. Poincaré, who was first one to have the intuition, he wrote a monumental work called La Mécanique Céleste, Celestial Mechanics. And I have one friend who has read the book, who is an amazing celestial mechanician. He predicts the future of our celestial system over millions and billions of years. He had a journal club that read it in Paris because they're very cultivated in France. They spent 1 year reading the book, but basically none of us read it. Now, one thing about a book is that it's obvious when you listen or read Poincaré that he had visual image of what he was doing, but he's very proud that in his book, he doesn't have a single illustration. The effect of this is that it took until 60s for physicists to run things on home computers to start understanding, Poincaré wasn't so stupid after all. There was something going on.
Thanks to the Second World War, inhuman effort was made to devise more efficient ways of killing large numbers of people. And part of it demanded designing very fancy weapons, which could not be designed without computation. So out of this came the first computers, and they were amazing. They were a real quantum step compared to what we had before the Second World War. And already by 46, already by the peace times, and so the physicists found ways of using the computers to test some deep ideas in physics. The first application was called Fermi-Fasta-Ulam model. So Ulam is the father of hydrogen bomb, a mathematician, and Fermi is one of our greatest physicists of last century. And they tested fundamental idea of statistical mechanics, which is the equipartition of degrees of freedom for statistical systems. And the first thing that came out was totally amazing. It turned out it's totally wrong. Equipartition doesn't work. So very first attempt to use computers of that kind. By 60s, if you were in a good institution like MIT, it was already possible to get research computers. So one problem up today and forever was to understand weather. So a student of Birkhoff, the greatest American mathematician, at least in a field of ergodic theory of the last century, a student of Birkhoff took a job in Department of Meteorology, or whatever it's called at MIT, and was among the first people to get access to digital computers. Or maybe it was even analog, I don't remember what the computer was. So his name was Edward Lorenz. He's actually a very good mathematician, but as far as anybody knows in popular culture, this is a weather person. He did something which we'll do in this course very much. He started as a very complicated system, which is a fluid dynamic system of flat Earth being heated from above with a layer of fluid, which is air. And in 19th century, the equations were written early 20th century, called Boussinesq equations and similar equations, which explain what happens when you drive air by heating a flat surface. And what happens is convective rolls set in, and then if you hit it too hard, things go turbulent. So he tried to put this on computer, and the way you put this on computer is explained in a section in a book called Life in Extreme Dimensions. Is for this problem, it's natural to go from partial differential equation that describes the fluid to a set of coupled ordinary differential equations. This happened by going from spatial representation of the fluid to its Fourier transform, which is nothing fancy, just a linear organization of degrees of freedom. But it's very elegant because it has to do with translation degrees of freedom. So one gets a large set of coupled equations. Today we solve them very well, and we find out that interesting problems that require between 100,000 and million degrees of freedom, but the computation, the algorithms, and also the computers themselves improved so much we can do this. But in '63, this was not an option. So what Lorentz did is he wrote these equations, and then he kept eliminating degrees of freedom so he could stick it on computer. Eventually he had 11 degrees of freedom. He stuck it on a computer, and he looked at numbers that came out. He discovered that out of them, 8 didn't seem to do much. So he eliminated those, and he ended up looking at 3 partial coupled equations. They're very easy to write. There is a state space, and now the state space is in 3 dimensions because only 3 degrees of freedom are kept. And we have our equations of motion, which is some truncation of Navier-Stokes equations that tell us that if the fluid is some state, this is how it evolves infinitesimal in time. And in more detail, he wrote x, y, z. So 3 degrees of freedom, which is 3 Fourier coefficients. But by this time we have forgotten all about where the model came in, because this is such a dramatic truncation that it has no predictive power as fluid dynamics. But turns out to be extremely important as educational tool what nonlinear system can do. And that's why we appreciate his work. He was not the first, but his work was influential in a well-deserved way. So the big deal about these equations and why you don't get them taught in your differential equation course as an undergraduate, because they have 2 terms here which are second order in the variables. So this is an example of nonlinear set of ordinary differential equations. And they're quadratic because original Navier-Stokes had a term which was called convective U gradient of U. So by the time you do this in Fourier modes, you end up with something that couples Fourier modes. So if they were not here, then anything one learns in engineering differential equation courses will work. You would do some Laplace transform and just solve this equation. However, this being the real world, none of this stuff works. You have to look at them. And what he did is he put them on computer as the first person to do so. Again, not really. Dame Levi Cartwright and mathematician Littlewood did that first in the war effort in Great Britain in the Second World War, where they were studying Duffing equation or designing radars. So they discovered the essential thing. And what he discovered was he put it on a computer, and what he started with some initial condition, and the thing did something. And what was all the revolution is just the fact that he looked at the trajectory visually. This was very hard to do. So in 1906 or something, there was a Norwegian physicist who was also an atmospheric physicist. He was interested in aurora borealis. So he was developing motion of charged electrons in magnetic fields. And he had a bunch of graduate students which are called amanuenses, people who did things with hands. They numerically integrated a very simple equation. And it took several years to produce a trajectory that on this plot would look like this much. And there was years of work in that time. So it's very hard to understand qualitative nature of these solutions at the beginning of the century when Poincaré and other people did influential work. By 1963, he could run it, and he discovered that it did something, and then it did something else. And then it seemed to do something that looked like something that happened before, and it kept doing such a thing. You've probably seen this picture. It's called Lorentz attractor. Now, what puzzled Lorentz, he was intellectually primed to understand this problem and not disregard it. Simulations were still rather painful because he had to look at numbers and plot them on a paper. But what puzzled him is that he would restart the computer and he would get different solutions. And then you would think that's just problem of numerics. There's some problem of round-off errors and something. But he was so smart to realize that this is a fundamental thing. So that's why we like it. And this course is a follow-up on his insights and Birkhoff, his teacher's insights. And what I want to emphasize today is not that it looks complicated, but if you run it for a while, you realize that this thing has 2 ears. It looks like a butterfly to him, but it looks like somebody has 2 big ears. So why is that? And if you run it longer and longer time, they look more and more similar to each other. So what's going on? Now, in this course, we tell you whenever you have a problem and you're given a set of equations, you're first supposed to find equilibria of the problem. That's the first step. Find the solutions in which the left-hand side vanishes. So 0 equals this gives you equilibrium. In 3 dimensions, that's a problem you can solve numerically. I mean, you can solve actually analytically. It's simple enough. This is bilinear. You end up in some fancy way with some quadratic equation. And you find that there are 2 solutions. There are actually 3 solutions. There's kind of a trivial solution that says if everybody is 0, that's an equilibrium. So there is equilibrium here. You divide your equations by that solution, and then you find there's a quadratic equation you're solving. And the next 2 equilibria, let's call them 1 and 2, the analytic form is plus minus square root of b rho minus 1. Now, this is a parameter that vaguely has something to do with Reynolds number and heating, original physics, but it's so far away from the original physics that you shouldn't take them too seriously. So there are just 3 parameters in these equations. And where the equilibrium is depends whether rho is larger than 1 and stuff like that. But the main thing you notice is that they sit on x equal y diagonal. So now you can plot them, and you discover the reason why you see 2 ears is that EQ1 and EQ2 are the same solution, just with a plus or minus sign. So now what you are discovering, you're discovering there is a symmetry in equations. Somebody handed you some equations that look like God knows what. And this is the simplest possible set equation ever. Usually you get a page of equations, and you will have no idea. On the 5th floor, for example, it took us several months to discover that Navier-Stokes equations that we're looking at have a symmetry. And we did it the same way. We did numerical simulation, and we found out that long-time solutions look symmetric, but we didn't understand why. So this is a very typical situation. When you have some law of nature, it might have some symmetry you're not aware of. But having it, it's a big deal. It's very helpful. And this is the simplest example.
There is a trivial solution, because when you look at the equation, all the terms on right-hand side of Lorentz equation are at least linear, and several of them are bilinear or higher order. That means if you set them all to 0, all the velocities are 0 on the left-hand side. And that's a definition of equilibrium. So equilibrium is either like a bottom of the valley where you just sit there, or top of the mountain, you sit there, or a ridge, you sit there. So that's the center of the points which we were drawing on Tuesday. Now, how your neighbors move turns out to be the big deal in equilibrium, and that's the next thing you have to do. You first have to do the equilibrium, then you have to understand its stability, and then you start piecing together the big world. And it's nice. I mean, you're interested. I'm interested in turbulence. So everything is going bananas all the time. Nothing is stationary. The clouds behind should be changing, but you just have a stationary picture. However, the most important thing are solutions of your equations where nothing happens. It turns out they're like, little pins around which you put the ears and you reorganize the whole world. So that's, general strategy of solving this, guys. You first find equilibrium, then you find something else. And that's something else I will not ask you to do in this course. That requires work.
The main idea, and that's probably the idea of Poincaré, was once you realize that the ancients were wrong and our world is not an exact clockwork in which I make an astrolabe and everybody just turns exactly with their periods, and 27 of these things turning, that's the clockwork of our world. No. The generic behavior in generic dynamical system is that you can hope not for exact periodicity, that's a rare probability zero event, but you can hope for close recurrences. And for government work, that's good enough. If you need to solve some problem to precision 1%, or 10 to the minus 11, if you're doing, particle physics or astronomy. You just have to work hard enough to find something that started in some neighborhood and after some time re-enter the neighborhood with precision of 1%. That's called a recurrence. Now, once you start about recurrences, you realize there are two kinds of behaviors that you care about. There are some points which wander. Wandering means is I start someplace. For example, I start on the top of a hill and the soccer ball rolls down. And it does something, but guaranteed never to roll back to the top of the hill because it's lost some energy to the friction. So that state, well, this is part of a state space. I'm allowed to start on the top of the hill. It'll be part of a wandering set. Initial points which start out as transients are never revisited. What's very interesting in dynamics is so-called non-wandering sets. So this is a set of all points which are recurrent. If I wait long enough, I'll come to their neighborhood with some precision. And it's these non-wandering sets which are the key of understanding. So now we are much clearer than we started. First we said, okay, solutions are fixed, periodic or aperiodic. Well, aperiodic we can split into wandering, which we don't care about if you're interested in for a long time. We care about them sometimes for a short time, but then we can integrate them anyhow. So there's no problem. We usually can predict short-time future. But for long-time future, these guys are important. The important ones, the recurrent, the non-wandering set, and that will be the key to everything you want to do. When you have this notion of non-wandering set, you get another thing that's intuitive. We always saw it when we looked at Duffing. So what happened when we looked at Duffing here? We found out that no matter where we start in the space, we either end up here, attractor 1, or we end up here, attractor 2. So in that case, the limit set of long-time behaviors, the non-wandering set, is very simple. It's just 2 points, which are attracting points. And the only probabilistic thing or imprecise thing is, being sure that you end up on one or the other and wondering how you're sure that. But in general, we can see that there will be some notion that it doesn't have to be just a point. It's very easy to find biological systems, for example, which are driven by some pacemaker like your heart, in which you start, excited, but when you cool down, your heart just does the same periodic motion. And in that case, the attractor is called a limit cycle. In state space, it's just a curve that repeats itself. But turns out that if your dynamics is higher than 2 dimensions, you need to specify for state at least 3 numbers or more. The generic situation is that you get something called strange attractor. The world splits into transient wandering condition and then set of states which are being revisited by recurrent trajectories called the attractor. With it comes the notion maybe of basin of attraction, meaning that all initial states would fall into that attractor and the other one. And the attractor can be fixed point, it can be periodic orbit, or aperiodic, in a sense, non-wandering, that will be more specific. Or, and that you also know, it could be any combination of the above. So, for example, if you start your life in Copenhagen, you're most likely that your fixed point will be cemetery in Copenhagen. If you start your life in the United States, it could be any place on a very large set. So there is, in the same state space, initial condition, born Copenhagen or born Gary, Indiana, you will end up someplace, but the attractors might be distinct. So I might have any combination of attractors. When that happens, it's obvious that I want to split my problem in individual problems. What happens to Jens Jensen in Copenhagen and what happens to John Smith in Gary, Indiana? Solve this problem separately. Strange attractor was something that was intuited by Poincaré, and he said, the thing is so complicated, I will not even attempt to draw it. And that actually kept this very deep and important mathematics from engineers and scientists for a century or so, because before the advent of computer graphics, it was almost impossible to have any visualization of what these attractors look like. Poincaré couldn't do it. Before him, Maxwell and Boltzmann were around the same time. They also thought about unstable motion strange attractors as foundations of statistical mechanics that also could not be visualized. Today we can track 1 million atoms. It's a totally new ballgame. And today these things that look like just bad experiments are now focus of good experiments. And Ruel and Takens gave them a cute name, strange attractors. So in previous video, we talked about possible kinds of flows, and I said, a flow can be not recurrent, not exactly recurrent, aperiodic. It can, but non-wandering, meaning that visiting a set of points called strange attractor, and idea sounds plausible, but what a strange attractor looks like. That answer was first given roughly in 1946-47, after the Second World War, where Lady Cartwright was the first one to actually plot a strange attractor. That strange attractor had to do with Duffing model, this vacuum tubes, because during the war the radars and lots of electronics became important, and pure mathematicians were employed by military to solve this kind of problems, practical problems. So then the strange attractor was glimpsed by various other people who kind of visualized it, but it was not persuasive to the woman on the street because, it was some kind of fancy mathematics. until a person who was a humble weatherman, Edward Lorenz, plotted the first strange attractor. Now, what happened to Edward Lorenz, he was trying to predict the weather, and weather is governed by Navier-Stokes equations. So the simplest weather is you have a flat planet, and there is a flat atmosphere on it. The sun hits the surface of the planet and sets convective flow in this flat atmosphere. So those equations are easy to write down, but they're partial differential equations, and as they describe every particle, in individual mass particle in the fluid, they're infinite dimensional. So what people do is there are various tricks called spectral methods in which you say, well, the solutions look smooth like waves, so let's expand them in Fourier modes, and let's approximate this by first 1,000 Fourier modes. Now, when Lorenz worked, that was undoable. You could not integrate 1,000 Fourier modes. But he was a rich man because he was a weatherman at MIT, and MIT was one of the first places to have computers. So he was able to radically simplify this model, in process losing all the meteorological significance of it, but reduce it to 11 equations, which he could put on a computer. And computer told him that after a while, actually only 3 of these 11 equations were showing signs of life. So he was actually able to throw away 8 of these dimensions and write 3 simple equations and put them on a computer. Now, this was rather difficult work because computer used to just produce numbers. So out of a computer came a paper, long paper with sets of 3 numbers. And Lorenz looked at these numbers, and they looked sensible. It looked like some kind of oscillation.
And also, there's a school of teaching due to great mathematician Hilbert, who says, when you teach it, you have to say it not once, not twice, but 3 times. So you're suffering through me repeating myself for the second time. Apologies.
So what he saw first was that things were just moving like this. That's what you expect. You expect some kind of oscillatory motion of waves, fluids, etc. So that was just fine. But then, to his chagrin, every so often, the thing did a wild jump, boom, to the other side. So suddenly x turned negative instead of positive. He had 3 variables, x, y, z, and we are showing you only 2 of them. And then the thing kept doing something, and then it jumped again. So it went from here, boom, and did this again. Okay, so that could happen. You have a system which goes right, 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 and then goes to left, 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 right. So he started looking at sequences of how long it oscillates left and right, and that looked random. There was no rhyme and reason. So he thought his program was wrong. So he worked very hard, etc. Now, the real truth about Edward Lorenz, he was not a humble meteorologist. He was a PhD student of Birkhoff, which maybe was the greatest or one of the greatest American mathematicians of first half of 20th century. And Birkhoff's specialty was ergodic theory, or understanding complicated behavior or dynamical systems. So Lorenz realized that this is an example of ergodic system, and he analyzed it as a mathematician would, but as meteorologist, he wrote it down in a paper you can read today. It's a beautiful paper. It's totally understandable. And he explained that this behavior is not error of computing. This is intrinsic to nonlinear dynamics. And in our course, we will find out a very detailed way of explaining why and how to describe it when it happens. So he produced a very concrete example of strange repeller that anybody could see a picture of. And that had tremendous impact, even though many other people have discovered it before. So out of this came this story about the butterfly, that the flap of the wings of the butterfly will, cause a storm in Pacific Ocean or something, which is nonsense. And he didn't invent it. Some other people said it first. But, what it says is that very small changes of initial collision when you have a strange attractor produce in finite time such large differences that implication is that the weather is unpredictable. That is to say, no matter how many computers we have and how many thermometers and how we control the sun shining, etc., the weather is unpredictable. So that was a very fundamental result. It's not because we are sloppy or unable to account for all the details. It is unpredictable because the unstable dynamical systems are unpredictable in a following sense, that if you have finite precision, no matter how small, you might be able to specify the state of all planets in a solar system is an angstrom precision and angstrom per second velocity, because on computers you can do this. Nevertheless, the future of solar system will be unpredictable. But, then you ask yourself some more specific question, when does this kick in? And that's where you start really learning stuff.
When you're saying it's unpredictable, what exactly do you mean? You're talking within a certain range? Meaning we can predict the orbital motions of celestial bodies, and we can predict the weather. You're just talking about the precision?
The very profound, deep understanding of what we learn in nonlinear dynamics as opposed to linear one is that there is a distinction between an ideal number like pi specified to infinitely many digits and pi specified to 11 digits. They're profoundly different because one of them is a point in a state space. The other one is a neighborhood in a state space. Because whenever you have any finite precision, now this is not the issue of computers, it's conceptual. It says there's a difference of how you study evolution of ideal Platonic, infinitely precise numbers that to, integer one, to infinite precision, but if you measure it, it to, whatever measurement you're using. So there is a profound difference between talking about clouds of points or points, and you need different description for two. Now, when you taught mechanics in courses that you have taken or should have taken, then you're usually taught mechanics of things like harmonic oscillators, which are stable systems in the following sense. The ideal solution of harmonic oscillator system, and you have done this when you studied normal modes, but ideally it just goes on a circle or ellipse or something. Now, if you perturb it a little bit, what happens is that perturbation doesn't grow, it just oscillates around forever. So when you're taught that kind of mechanics, you don't realize that there is a difference between perfect oscillator or, infinitesimally imperfect oscillator, because it's just, the error doesn't grow. But we have learned that there are two kinds of solutions to linear differential equation, which is what happens to neighborhoods of all trajectories in any dynamical system, any evolution. either solutions are complex pairs, so they have oscillatory property, or they are real exponents which are either negative or positive, which means either stuff dies for negative one or explodes for positive ones. And now it turns out a typical dynamical system is mixture of all the things. There are positive, negative exponents. Roughly speaking, when you create a typical dynamical system, which you create because you're doing something in a lab, building a model, trying to understand COVID-19 as differential equations, you have lots of parameters, you juggle these parameters, more or less a random from point of mathematics, and you'll find all these kind of solutions in it. And you will find that you have unstable neighborhoods, oscillatory neighborhoods, contracting neighborhoods. And what happened to Lorentz, he found out that the ears and the nose, the third equilibrium of portrait of Lorentz, they are all unstable. So what their dynamics says is the following. I come close to one of them, it's unstable. So, I get sucked in because there's some stable direction. I get thrown out and I fall someplace. And, usually I fall close to one ear or the other one. And I think, I can find peace there because that looks stable to me. So I keep getting closer, closer, closer. And I discover, no, there is an unstable direction. I get kicked away. And, I end up being a ball that's being kicked by these three unstable equilibria. And that's the mechanism that creates these chaotic behaviors. You don't see it in points, but you see it any open neighborhood, any cloud will experience this. So the fundamental thing is to understand you think of a flow as clouds of points and not individual perfect points. So that's how I see it. I might be wrong, but that's my understanding.
If you have the notion of like the butterfly effect or chaos, right? If you change the initial conditions a little bit and get a very different result, and so it's the outcome is based on the precision you have, and if it's the case that the precision in our physical world is limited by quantum mechanics because we have an inherent uncertainty, does that mean that the universe is inherently indeterministic?
Now we have to be very careful about words. And it's not philosophical, it's really fundamental to understanding what laws of nature do. When we talk about classical Newtonian physics, by deterministic, we mean two things. One, that every state of the system can be specified by a set of numbers. So I have a state space in which a point is a unique thing in a state space. What the law of motion does is it traces out, future of that particular point. And in principle, it does it with infinite precision. There could be some computer problem in implementing it, and there are, smarter or less smart ways of doing these integrations. But determinism means that I know everything about what's possible. This is a state space. And I know my law, and law is true. Newton makes no errors. It's just true. And quantum mechanics has nothing to do with it. And also stochastic processes, which is effect of external noise, has nothing to do with it. So that's called deterministic chaos. In systems, the big shock for lots of people in the 60s and 70s, having been taught otherwise, in their very fancy educations as physicists and mathematicians with serious education and serious work behind them, was to discover that fundamentally, even though the laws are perfect and the specification is precise, I'm not omitting any information about my states, I still cannot predict. Now, this thing about how precise I am, there is a number, and the number basically says that there is a size of initial ball of conditions, call that epsilon or delta. And then you multiply it by our exponential e to the ta, the exponential we keep computing. And this number, if exponential has expanding parts, this number always exceeds 1 and does it exponentially fast. So it doesn't really matter very much whether I specified with precision 10 to the minus 3 or 10 to minus 4, because very soon in both cases, as we know again from COVID-19, we'll get to the threshold which is unacceptable in both cases. It'll take 3 seconds instead of 2 seconds because it's an exponential process. It's still seconds or days or weeks or something. So that lapun of time is not very important. What's very important is that, the rate at which you lose information. And, that's intrinsic to the system because that's described by this eigenvalue up there. So it's true that different initial precisions enable it to go a little bit longer. So you can predict whether 4 days instead of 3, because you're using 1,000 times more computers, but predict 5 days instead of 4 means you have 1 billion computers. You cannot beat exponentials. There is no herd immunity against stupidity. You just can't do it. You have to develop things to deal with. And so what you do about nonlinear physics, you start learning the geometry of possible outcomes. Once you understand that you cannot specify precise exact outcome for my initial conditions, then you have to learn what are the possible outcomes that are allowed. And, that's the essence of the theory. It describes the range of possible outcomes. And that's what you use when you do send spaceships out. You find out that you can get here and there, and then you know how to implement control or correction of the course once you understand the geometry of state space. And geometry of state space is not lines, it's not hyperplanes, it's manifolds. It's curved, and that makes it harder to do.
Okay.
See, I'm very emotional about this. And I'm losing the class. Few people have checked out. So I should probably shut up and continue.
So now the big thing, and there is nothing else to do. It's a wonderful thing about modern age for last 30 years or so. We are able to actually take nonlinear differential equations like this one. So this Lorentz equation, which is supposed to model, pressure, temperature, something. This equation has one term, which is not linear. And it has a couple parameters which have vaguely physical origin. But I will not spend any time on explaining its parameters. Basically, the role of these parameters is you can see if sigma is negative and very big, you can see that this differential equation will experience lots of friction and system will die. So what these parameters describe is roughly how unstable the system is, and Lorentz used 2 values and produce this picture, which you will produce in your simulation because it's easy to do. Now, without understanding this picture, there is no way to understand nonlinear dynamics. So you will have to learn how to compute. This is not for gentlemen. This is for people who work. Another example, which is very popular, it was designed by a very gifted chemist called Rosler, who was classically trained. He reads Greek literature, etc. And this is Germany, where they still have classical education, or used to when he was young. And this system is supposed to explain how you make toffee. When you go to amusement park, how you mix this thing that then you can eat as candy. And with reasoning, which please read in the book some explanation of it, Rosler designed 3 equations which capture essential features of Lorentz flow, but are simpler to analyze than Lorentz flow. So there are 3 variables, and there are 3 parameters, and the system is nonlinear because there is this combination here, which makes it bilinear or second order in the variables. And again, you put this thing on a computer, and as it's always true of equations, but nobody, the real truth about equations, you have no idea what solutions. When you look at these equations here, given to you by Rosler, they're simple. They can be derived on simple phenomenological grounds, but you have no idea what the long-term behavior of this is. So put it on a computer, as you will do, and you discover that the thing does something like this. It goes up, it falls down, it goes up, it falls down, it goes up, it falls down. And it seems to do this forever. As a matter of fact, we cannot prove mathematically in this case that it does it forever, but for these particular values of parameter, the system seems to be never approaching any limit cycle. It just has this behavior. So that's the simplest example of differential equations that exhibit what we'll call chaotic dynamics. The previous one of the 3-disk billiard was the simplest example of maps that exhibited. And now I've told you, whenever you have a dynamical systems, the first thing you should do, if I haven't told you before, I tell it to you now, the first thing you should do in a dynamical systems, you should solve for equilibria, which means you should set left-hand side 0 of this equation to 0, and solve for the places where velocity field is 0, so you don't go any place, you stay there forever. They call equilibria. When you do this, and you will do it, it's easy to do, you discover that this system equation is bilinear, so it can be made to look quadratic. This system has 2 equilibria. There is one here, one here, and there is another one here. So this is lower equilibrium, upper equilibrium. And nothing happens at them because they're stable, but you notice that in their neighborhoods seem to care about them. So they play some role. It'll turn out they play a very crucial role, as we will show, in shaping the dynamics. And it turns out this equilibrium has to do with swirling the points around. So trajectories swirl around. And this equilibrium turns out to define the basin of attraction. So there is some kind of wall here that contains this point. And everybody who is close to this point, but on this side of the wall, falls into the attractor. And everybody who is away falls away. So this is actually the border of the basin. So in this very trivial example, you see already intuitively that equilibria might play 2 important roles. One is it shapes the flow, and the other one is it separates the things that belong to attractor from things that run away. And this seems to be an example of what I told you was called strange attractor. You run it. This is run for some time. There are arbitrary units, but eventually you understand how to get a unit of time. So eventually you will see that some units that you'll learn how to interpret. For time as long as we want, this never settles down. So that's our working example of strange attractor.
It's really interesting I find what's really interesting is the way it like goes up and then swirls down and keeps going up. I don't know what physically would do that.
Agree with you. Yeah. So that's effect of nonlinearity. Now, you can see that when it's starting to spiral out, it's in a plane.
Mm-hmm.
So close to equilibrium point, this description in terms of hyperplanes and linear spaces, we said manifolds is a tangent bundle. At every point you have a plane. That's actually quite good description for quite a while, long distance. Because attractor, you go half attractor, it looks like a plane. And then you hit the wall. That wall is due to the other equilibrium. Because it's nonlinear, you need a curved surface to contain both of these guys. You cannot do this by a plane. So you come there and you get kicked up. So I try to, if you read the text in the Chaos book, I try to explain how it works. But, you get a little bit too far away and then suddenly you get kicked out and you go because of the other guy, you go up. And then you lose steam and you fall down and you keep doing it. So you're just being kicked around between these two equilibria. They're both unstable and they don't let you ever find peace. You're never allowed to fall asleep again. Now comes a very personal question.
Now, computing is a dark art, and it's a very personal art. It's like personal hygiene or something. So, Charles Babbage, who invented computers, has been asked by members of parliament, not so different from US Congress. In England, they were hereditary members, so they were not selected for their intelligence. He's been asking, okay, you have this figure, but if you put the wrong figures in, wrong numbers, will the right answers come out? And Babbage was left speechless. Lots of you today compute unquestionably, so you are like members of the parliament. It's not only that you have to program something or use some prepackaged language like MATLAB or Python or something. You really have to understand what you're doing, especially in a case like this, where you have to understand whether your answer is just because you're programming badly and you have errors, or the answer is really intrinsic to dynamics. So chaotic dynamics is a region where computing is important, so please take it seriously. So to summarize so far about dynamical systems, what we have learned, dynamical system could be either flow-emitter and map, is a pair. It's defined by state space, law of motion. State space is lots of points, but the law of motion splits it into orbits. So a dynamical system is really a bunch of spaghetti. And if you can organize this spaghetti, understand everything about dynamics. And the key notions of doing it is you're interested in recurrences in long time, because if something happens once and never happens again, there is nothing to predict. So you care about recurrences. And the technical word that you care about is the non-wandering set of F, meaning that within this world there's some special points to blow them up. There's something that maybe looks like this, which is restricted to a subset of the whole space, which is called strange attractor. Now, you always live in this world. For example, if you take a cup of coffee and you're turning it around like this, you know that the molecules of the coffee will not go to the speed of light. So there are possible states where fluid moves at any velocities, but you know that your system will be in sub-state of all possible states. that could be a strange attractor.